Well, you guys participated in the contest, but for anybody who is watching this on YouTube or wherever else it gets posted, there was a contest held on April 15, 2012 at the University of Chicago. It was a practice contest for all of the teams that had earned a berth at World Finals of the ICPC. I was the chief judge for that contest, and I'm going to talk a little bit about the problem set that we used in that contest and how you might approach the solutions. Several of the problems can have multiple solutions, and I'll talk about the one I'm most familiar with. But if you see another way to solve it, you may be right. There may be multiple ways to solve different of these problems. But the first thing I want to do is acknowledge those who helped me. This is the judging committee, and this committee worked for about 6 weeks to put together that problem set. Evaluating problems, solving problems. My director has just told me to move to the right a little bit, stage right. Solving the problems, evaluating the problems, generating opinions about the problems, generating the judge data, testing the judge data. There's like a week and a half to 2 weeks at the end that are spent solely on quality control to evaluate the statements of the problems, to make sure the judge data is correct. So I want to thank these people quite a bit for the amount of work that they put in. The top two particularly, Tom Connerly and Mark Gordon, put in tremendous amounts of time to help make this problem set as good as it was. I think the problem set was a success. There were some things, no problem set is perfect, there's some things that we'd like to do better. But overall, I think that the difficulty level was exactly where it needed to be. I think that the cleanliness of the data was perfectly clean. And the problem statements, there were only about 10 clarifications issued throughout the contest, and almost none of them were about the statement of the problem. So the statement of the problems were clean. And that's a trifecta right there. That's really what we shoot for. And so this was thanks to the folks whose names you see up here. It was a successful problem set. So I'm not going to talk about this first problem very much because it's the one that I did not solve. Mark and Tom solved this and worked this through to conclusion. I was a little nervous about this problem. Cosmocraft, if you haven't read it, described a game and asked you to determine the optimum number of armies that you could have at the end of this game. And I was deeply worried that we could come up with a good strategy, but the teams could come up with a better strategy. How can we confirm that our solution is the best one? And Tom and Mark did a great deal of work to theoretically analyze the game and come up with some proofs for some of the things you see on the board. They also wrote a dynamic programming solution which was too slow to be judged correct, but nonetheless could be verified and could verify that our judge data was correct. So we were confident in our judge data. And in fact, every problem that we gave you, there were 2 separate judge solutions for that problem, just to verify the data. And Cosmocraft is the same, except one of those judgments is not mine, and so I can't speak to it as well as either Tom or Mark could. But I can tell you these things. First of all, there's no need to stockpile money. And I'm not going to describe I'm going to assume a knowledge of the problem. You can go to serjudging.vanb.org or to the UChicago homepage to get a copy of the problem set. There's no need to stockpile money. You're better off buying workers, because workers, the next turn, will turn into dollars. So if you hold on to $5, you've got $5 next turn. If you buy 5 workers, you've got $5 next turn, plus an increasing amount in following turns, because the workers generate money. The second is you should build as many workers as possible as early as possible. So at the beginning, if you have 10 workers and 7 production facilities, you should build the max you can, which is 7, and then use the remaining 3 that you couldn't build because you didn't have as many production facilities to build more production facilities. And once again, Tom and Mark proved that this was an optimal strategy for maximizing your amount of resources through the game. You should wait as long as possible to build armies to counter an attack. this should be kind of obvious. You want to build up resources, build up resources, build up resources. Building armies early instead of workers detracts from the amount of resources that you can build up over time. So you want to wait as long as possible. So you should build those those armies either in the last turn before an attack or the last 2 turns before an attack. But you can show that if you go any further back than that, you're actually hurting yourself by building too many armies, not enough workers, not enough resources. The amount of armies that you can build actually goes down. So that gives you a strategy of simply going through turn by turn by turn, and at every turn determining how many armies you need to build. Maybe you have to step back a turn, but after you build your armies, use this optimal strategy to continue to build workers. There is a special case, and I'm not quite sure how they got around it, but there's a special case of when you are attacked 2 turns in a row. But I'm sure if you think about it a bit, you can come up with a solution. And I'm sorry I can't be more definitive about it, but as I say, this is the one problem that I didn't solve. Any questions that I might be able to answer? Nobody submitted this problem in contest.
Very greedy-like strategy, right?
Pardon?
It's a very greedy-like strategy.
Exactly. It's a greedy strategy.
So the difficulty of it was to prove for the contestant that it was a valid strategy. Okay.
The actual code is relatively simple.
Yeah.
Proving to yourself in your mind that it works is the intellectual challenge.
It seemed like this huge optimization problem where you had to set up all these systems of, linear equations or something and minimize. That's what it seemed like.
It did, and as I say, when I first approached this problem, was worried that I could come up with a great strategy, but how do I know it's the optimum strategy? And I'm sure contestants felt the same way. They're reading through and they're thinking, I know some ways I can do some good things here, but how do I know that it's the solution? So nobody even tried this. We had 0 submissions of this problem. Okay. So let's move on to the next problem. Covered walkway. Oh, I liked covered walkway. So you've got positions along covered walkway, and you've got a cost function. So if you want to cover from I to J, the director's moving me over again. I need to put like a tape X on the floor,
like a star on the floor.
My mark.
Maybe that orange slip of paper or something. Or do you want this?
On the table that you... I'd probably trip over that.
Yeah.
But you've got points on a number line, and you want to cover them. And the cost to cover from point X to point Y is some constant plus the difference squared. So you want to optimize. You could cover the whole thing, and the cost would be C, the constant, plus the biggest value minus the smallest value squared. You could cover each one individually, and the cost would be simply C times N, however many things you had. So you need to figure out the optimum way of covering these things. Well, there's a fairly simple order n squared dynamic programming solution. We'll take a look at it because our solution will stem from it. But it should be noted that this solution is too slow. This will not finish in time. But it's a good place to start. So for each a sub I, compute the best that you can do at I is the minimum of what would happen if you went up to j and then broke between j and j plus 1. Okay, that's really all there is to it. So to compute that, all you really need to do is iterate through the i's, iterate through the elements. Then for every one, you've got a j loop that looks before it to find where the best breakpoint is. Okay. That's an order n squared algorithm. Really simple. If the numbers were small enough, I'm sure every team that competed would be able to crank this out in 10, 15 minutes. The problem is that the number of numbers can get up to 1 million, and you can't do an n squared algorithm. It has to be order n log n or order n or something much faster. So let's take a look at how we can make this faster, how we can find those things more efficiently. So we need a more efficient way to compute that best of I. Well, suppose that we've got two numbers j and k that are less than I, and we're trying to compare them. We're trying to see which one would be the better breakpoint if we were up at a sub I. So do I want to go up to k and then go k plus 1 to I? Or do I only want to go up to j, break it there, and then do j plus 1 to I as one big covering? Which one of those is best? Well, there are the formulas, and I've got a question mark there to indicate that, we want to compare them. We want to know which is greater than, which is less than. So this is the formula, best of j plus c plus the difference squared. How does that compare to best of k plus c plus that difference squared? Well, we can carry through the multiplication of these squares, and we get this monster. Well, we're trying to compare this trying to compare j to k. No matter what j and k are, c and a sub I are going to be the same. They can't contribute to the difference. They can contribute to the actual value, but if you're trying to compare j to k, they aren't going to make a difference. Both j and k have a c. Both j and k have an a sub I squared, so we can just get rid of those. So since c and a do not contain j or k, they can't affect the comparison. We get rid of them. We get this guy. So best at j minus 2 a sub I a sub j plus 1 plus a sub j plus 1 squared. How does that compare to the same thing with k? We good so far? Well, let's express that as a function of a sub I. That means that if we were comparing j and k, as we move forward with different i's, all we have to do is take a sub I and plug it into these formulas, and we can compare the two. That's all we have to do to determine which one is better. Just have these formulas, and as we move forward, plug a sub I in. Well, it turns out that those things are really simple when you express them as functions of a sub I. It turns out that they're simply linear. So you've got negative 2 a sub I, a sub j plus 1 times a sub I, plus that stuff, which is constant in terms of a sub I. How does that compare to the k of the same thing? So these comparison functions, the way to compare line j, or way to compare breakpoint j with breakpoint k for any I going forward, they're simply linear functions. Because they're linear functions, there are some nice geometric interpretations that we can apply to them to help us understand the problem. In particular, let's take a look at that, what we would call the slope, if we were to plot this as a line, which is the coefficient of a sub I. It's minus 2 times some positive number. So it's going to be very negative. And the higher I goes, remember the input states that the numbers are strictly increasing. So as I gets bigger, a sub I gets bigger. As a sub I gets bigger, that gets more intensely negative. So as we go further out, these lines get more and more and more negative in slope. Make sense? So that will give us a picture that looks something like this. So here are some lines. And there are these cusps where they intersect. Okay? So as we move forward with I, once one of them gets better than the other, once k becomes better than j, j will never get better again. You can see that from the lines. Once k becomes more intensely negative, once it becomes, and remember smaller is better because we're trying to minimize cost. Once this gets small enough, j will never be able to beat it again. And there's some cusp where k will overtake j, and so on and so forth. These things will form, let's see. So to find these things, it just simply becomes a linear walk. We simply walk forward through these things to where the a sub I we're looking for is between the cusps, and that's the one we use. So it's a strictly forward walk through these guys. Now sometimes when you add a new line, it will have a disposition such that it will shunt off other lines. So if this was the last line we added, then this line and this line will never ever be the best breakpoint. Because you can see we're going to go from here to here to here, and these guys are just shunted off. So that gives us our strategy. We move forward one by one until we find where our A sub I is between the cusps. Every time we add one, we're going to add it to the end. And then we're going to remove elements that have been shunted off. Okay? So every element is either going to get walked over or shunted off once. And that means that over the entire algorithm, our process for finding that minimum is order n. So now we've reduced the entire algorithm to an order n, and we can do a million things. Kind of a fun problem. Any questions? Is that cool? I kind of liked this. I kind of liked that interpretation. You guys got this right. Did you use an interpretation similar to this, or did you use something different?
It's actually exactly what you are talking about. We used the same stuff.
Okay.
Yeah.
Cool. So let's talk a little bit about double dealing. Double dealing was intended to be the second simplest problem in the set, but a lot of people had problems with it with time limit exceeded, which kind of surprised us. We had a C solution that ran in about 6 seconds on our judge machines, in our environment. And we had a Java solution that ran in 18 seconds. Because of that, we set the timeout at 30. And that, we got so many time limit exceptions that we upped it, early in the contest to 45. We still got a lot of time limit exceeded. You can't simulate this, obviously. The numbers are too large. You've probably heard me talk about programming by the numbers. Well, the numbers here go from 1 to 800. Why not 1 to 1,000? It should be a red flag to any good contest program. Wait a minute, why does this only go to 800 instead of 1,000? Maybe it's because the numbers get too big. And maybe if they get that big, I can't simulate it. Well, I think most of the competitors picked up on that because the problems were not with they were trying to simulate it. They were doing the kinds of algorithms we wanted. They just weren't terribly efficient at the various pieces. So there are 2 parts. The first thing you need to do is to form a graph, where every node in the graph represents a card in the deck. And then consider each node to have a single link, which is where that card goes through one deal pickup process. Okay? That, I think, is where most people had the difficulties. We saw all sorts of complex data structures being used, where a simple array is really all that's necessary. All you really need to do is go through like player 0's cards, players 1's cards, players 2 cards, and then put them in the deck, and all the players' cards are together. You just need to figure out what player 0's biggest card is, then subtract M, that's his next, subtract M, that's his next, subtract M, then put those in, then go to player 1, figure out his biggest card, subtract M, subtract M, subtract M, so on, and you can fill out that graph relatively simply. We saw people using hash sets and other kinds of very complex data structures that were probably leading to their timeouts. So you build that graph, and then you find cycles. A cycle in that graph of size n means that after n deal pickup operations, each card in that cycle is back where it started. So then it's just a matter of taking the least common multiple of the sizes of all those cycles, and that's your answer. Any questions on double dealing? Okay. This was intended to be the easiest problem in the contest, the end of the world. It's very simply given a configuration of a Towers of Hanoi problem, figure out how close you are to the end. So in case you're not familiar with the Towers of Hanoi, which I think just about any computer scientist who's at this level of programming is familiar with the Towers of Hanoi. But in case you're not, here are some interesting things. To solve a Towers of Hanoi with n disks takes 2 to the n minus 1 moves. So And to move a pyramid of size n, here's a pyramid of size n. It's got a pyramid of size n minus 1 on top of it. You've got to move that out of the way by moving it to the other peg, and then move this one biggest disk from the source to the destination. Then you've got this pyramid of n minus 1 that you've got to move from the other peg back to the destination, back on top of the biggest disk. It's nothing surprising. So, if the disk that we're looking at is on the source peg, that means that we haven't completed moving the disk pyramid of size n minus 1 off yet. So we've got to do that. Then we've got to take one move to move the big disk. Then we've got to take 2 to the n minus 1 moves to move the smaller peg, the smaller pyramid back. That's a total of 2 to the n. So we've got to take a look at all the remaining moves to move that remove that n minus 1 pyramid from the source over to the other peg, and then add 1 shifted by n, which is 2 to the n, add 2 to the n for once we do that, we move the big one and then move the smaller pyramid back on top. If this larger pyramid, if the larger disk is on the destination already, then we've already gone through a lot of that. All we need to do is move the pyramid of size n minus 1 back on top. Does that all make sense? You guys got this probably pretty quickly, yes.
So a thing that we noticed towards the end of when we were actually following it and how we implemented it is you can just by looking at what configuration you were given, you could basically compute a bit string that corresponded to the move number that you were on, or the number of moves that you had left.
Interesting, which would be the one's complement.
Yeah.
Of, yeah.
So all you would need to do for that is, if you start with B, B means that you're in the correct place you need to be in.
Mm-hmm.
You append a 0, and for every subsequent letter that's the same, you append the same bit, and anytime there's a change, you flip the bit that you're appending. Interesting. Yeah, that works out.
That is, I'm going to have to study that, see if I can figure out why that works out. That's kind of cool.
Yeah.
Okay. Is that the solution you used, or did you use the solution?
we use that. And that only works if it's solved perfectly so far.
Right.
If there are any diversions to that.
Then,
yeah.
Same thing here.
Yeah.
I have a question. Is how do you generate the test data to make sure like it is on the shortest path from the initial state to the end state? Yeah.
What I did was, let's see if I can remember how I generated the test data. I believe, used a modification of this function with all of its moving source to disk to randomly decide whether this disk was on its, flip a coin, half and half, whether it was on its source or its destination. So I took the biggest disk, randomly chose whether it was on its source or its destination. And then, depending on what the source and destination of the next disk ought to be, I randomly chose whether it was on the source and destination. And so on throughout all, however many there were, up to 63 disks.
Oh, I see. Yeah.
Is there a reason you kept the limit to 63?
Yes, because if you went up to 64,
right,
to the power of 64 minus 1 blows a
right,
long int.
Right.
We do not give big integer problems because there is a difference between Java and C++ in how they handle big integers. C++ has some big integer things, but they're not standard, you know. And if they're what you practiced with, if you practice with one set of big integer stuff,
right,
and the contest doesn't have that, then you're at a disadvantage. Whereas in Java, it's standard, and every Java programmer who does contests knows it. So we don't want to give Java programmers an advantage, so you will, in contests where I make the data, you'll never see big integer problems.
Now, is that equally applicable for World Finals?
I am not responsible for putting together the problem sets for World Finals. I would suspect the people at World Finals are really, really good at this. So I would suspect, I have tremendous respect for them, so I would suspect that they would feel the same way, but I don't know that from firsthand knowledge.
Good to know.
estimation. So estimation was given a very long array of numbers to break it up into partitions. Then use one number to estimate all the numbers in that partition and compute an error, which was the absolute value of all the differences. Okay. So the first thing that you need to do is compute a cost array, where costs of ij is the best you can do estimating everything from a to I to a to j with a single number. Okay. Once you do that, then it's a simple dynamic programming to figure out what the total optimal solution is. So we'll focus more on the computing of that cost sub ij. And this is a fun fact. For a group of integers a sub I to a sub j, the number which minimizes that error is the median. That seems surprising. It surprised me, but you work through it, it's true. Take like 15 zeros and a 20. The median is 0. You'd think it would be more towards the middle with a bunch of zeros and a 20, but it's not. And the reason is every time you take a step towards 20, you minimize, you reduce your error by 1, but you increase it by 19 or however many other zeros you have. So the median is indeed the best you can do. And so now we're on a quest for every single sequence, a to I to a sub j, to find the median. And once we find the median, it'll be easy to find that error cost. Okay. So the data structure I use, and once again, I've talked to other people who have used other techniques. So this is not the only technique. This is simply the technique that hit me. So built a complex structure that was a combination of a binary tree and a doubly linked list. The doubly linked list kept the numbers in sorted order. And kind of a fun thing, when you insert into a binary tree, if you insert to the left of the node, then that is, make sure I'm doing it right for you, yeah. If you insert to the left of the node, then that value is immediately to the left of that node in the linear list, or sorted list too. And the same thing for inserting to the right. If you insert to the right, then that number is immediately to the right of the other number in the sorted list too. So you can build a sorted list in order n log n time by just inserting into a binary tree and then just maintaining the links of the doubly linked list as well. Okay. So when we do that, we can keep track of where the median is. We can keep track of if this new value is below or above the median, and we can keep a count. And if it gets unbalanced, if there are too many below, we can simply use our doubly linked list to scoot back one, and that's the new median. If we put too many on the high side and we get out of balance to the high side, then we can simply use our doubly linked list to get our new median. And we can keep the cost as a running cost. I'm not going to go over, you can take a look at the code to see how it's done. But you don't have to go back over the iterate. You can keep the cost as a running cost. And then just record cost of ij. And as I say, cost of ij can be easily computed from cost of ij minus 1 rather than having to go back through the entire subsequence again. So and I also used AVL balancing to keep it efficient, even in pathological cases where all the numbers are already sorted. Binary tree, you'd end up with a linear list, but AVL balancing keeps it efficient. So here in n log n time, you can actually, it's n log n for every I, so I think it's n squared log n because you have to do this n times, for every starting point. But doing this, you can rather efficiently compute the costs. Any questions about that? That's kind of heady. The rest is easier. Is that cool? I need a nod from you. Yeah. I mean, there are this few people in the room you can't get away with,
not nodding.
If the room was full of people, you would notice. But with this few people. Well, once you have that cost is computed, the dynamic programming is pretty simple. This is the code that's actually in my code minus comments. just simply for every best sub ik is the best you can do, covering A0 through AI with k partitions. Okay. So 0 partitions isn't possible, so we'll just stick a dummy large value in. Covering it with 1 partition is simply the cost to cover the whole thing. And then for every I, we need to go to j and see what's the cost if I go up to j with k minus 1 partitions and then add 1 more partition from j plus 1 to I. Okay. So the dynamic programming part is actually, at this level, pretty simple. Cool? Questions?
How did you guys keep the median, Jiang and Arturo?
We actually used the segment tree instead of the balance tree, but it's the same idea. Yeah, but I want to mention something is like if the program is online instead of offline, like you are given a series of numbers, and you are, if they get curious about what is the median of a certain interval, there is actually a kind of data structure which is called partition tree, I guess. It will support this kind of operation actually.
Okay. So
for this program, it's also to do this, use partition tree to make it like n square log n.
Okay.
Yeah.
Well, for Juggler, there's a simple but too slow solution. And once again, I've talked to other people who had other solutions to Juggler. I'm going to tell you the one I used, but it's not necessarily the only right solution. I know other people who used completely different kinds of solutions to Juggler. But there's a very simple but too slow solution. You've got an array of integers that's a permutation of the numbers 1 through n. Wherever the number 1 is, that's the ball you want to drop first. Wherever the number 2 is, that's the ball you've got to drop second. So if the number 1 is here, you've got to figure out whether to rotate this way, clockwise, or counterclockwise. What's the minimum number of moves to get 1 down to your hand so you can drop it? If it's the first ball, it's trivially easy. It's just index math. Wherever I am, take the index of 1, the difference, take n minus that difference. That's the left, that's the right. Take the minimum of those. It's easy. When I get to the ball 2, once again, it's really easy, except that I've got to account for ball 1. So was ball 1 on the left or the right? So I can do the same index math and figure out how far it is from the ball in hand to here and how far it is from the ball in hand around the other way. But then actually ball 1 is in my hand, so this isn't a good example. But in future, you've got to figure out where ball 1 is and subtract that from the appropriate left or right. When you go to ball 3, you've got to know where ball 1 and ball 2 are to subtract them from wherever they are, left or right. Ball 4, you've got to subtract balls 1, 2, and 3. So that ends up being an order n squared algorithm, and that's too big. Well, suppose we were to reorganize that list. Suppose that we were to go through that list and move all the balls up to the front of the array. Just kind of push them and get rid of that empty space from balls that have been dropped. Then our first ball is once again just an index calculation. So we could do that. We could scoot things over and then do a simple index calculation. Scoot things over, do a simple index calculation. The problem is that scooting is an order n operation. We need to do that n times. We're back to order n squared. Okay, so what to do? Do you guys know what to do?
Actually, we use the segment tree for this.
Oh, okay.
Yeah.
So what if we only reorder the list sometimes? For instance, let's reorder it every square root of n operations. Okay? So we do square root of n operations, then we reorder the list. We do square root of n operations, reorder the list. Do square root of n operations, reorder the list. Well, that square root of n, when we go through that process is that same. You got to know where we're doing ball 2, you need to know where ball 1 is. Doing ball 3, you need to know where balls 2 and 1 are. That's order n squared. But since you're only doing it on square root of n things, that's order square root of n squared, which is order n. You do that square root of n times, so that comes out to be order n square root of n, right? So what about the reordering? Well, the reordering is order n. How many times do you do it? Square root of n. So the reordering is order n square root of n also. So it reduces the entire algorithm to order n square root of n. Kind of a cute little trick.
Actually, after the competition, I talked to one of the team from South California. They also use the same strategy like this one.
Oh, this kind of strategy?
Yeah, they use the same strategy.
Cool. Cool. You'll notice that a lot of the things that I am presenting, I'm not presenting a lot of advanced algorithms and a lot of advanced data structures. I'm kind of showing how to do this with more simple data structures and still get it done within the time frame. Okay. Well, I'll depart from that when we get to science, but we're not there yet. Red-blue spanning tree. So just use the standard Kruskal's algorithm, but you'd use it twice. Kruskal's algorithm is the one where that's for minimum spanning tree, where you take all the edges and sort them by size, and then you take all of the nodes and you put each in their own set, and then you go and you take the edges one by one, smallest first, and if it connects two nodes which are not in the same set, you union those sets. That's all there is to Kruskal's algorithm. So we're simply going to use Kruskal's algorithm twice. The first time we use Kruskal's algorithm, we're going to start with the red edges. We're going to go through all the red edges and link things together into sets of nodes. This will tell us which blue edges are necessary to connect the red components. Okay? So first we'll do it with the red. When we run out of red, if it's still not connected, then we'll use blues, and that will tell us which blues we have to have, which blues are necessary because the reds aren't sufficient. Okay? So first we'll do reds, then we'll do the blues, and we'll remember the blues that we used. Then we'll start completely afresh. We'll erase everything, start completely afresh. We'll start with the necessary blues. Then we'll fill in with other blues until we've got K. And then we'll do everything else with reds. And if we can get through all of this second phase with n-1 edges chosen, K of them blue, then we succeeded. Otherwise, we failed. Make sense?
Yeah.
Question?
Don't you have to make sure like the graph is connected at the beginning?
That is a promise in the problem statement.
Oh.
The problem statement does indeed say that the graph will be connected. Okay?
Yeah.
The red gem. The red gem. This was the last problem in the contest that was solved. Cosmocraft wasn't solved because it wasn't even tried. But this was the last problem in the contest that was solved, that got a solution in. Yeah, I don't know if you heard me. You maybe did. I cheered very loudly when someone solved this one, because it meant that every problem, except for Cosmocraft, it wasn't even tried, every problem that was tried was solved. That makes you feel good as a judge. That means that your judge data was solid. So we were, and that the problem spread was good. So we were very happy when this one came in. So the problem with red gem is you've got a big purple circle, and on this big purple circle, you've got a special red circle, and you've got a bunch of orange circles. You want to know what points on the perimeter, or what is the proportion of points on the perimeter of the purple circle that can see all of the red circle without being blocked by any of the orange circles. Okay, that's it. So if you take a look at these two sight lines, these rays, those rays are tangent to both the red and the orange circle, and the colors don't come out really well here, but this one is red, this one is orange. Okay? So if you take a look at these sight lines, if I'm here, I can see all of the red circle. If I'm here, the orange circle blocks at least part of the red circle. If I go up above that one, which I'm not tall enough to do, then I can see all of the red circle again. Those sight lines indicate to me, those rays indicate to me where this particular orange circle blocks at least part of my view of the red circle. So now what I've got to do is figure out where those rays are, and in particular I want to get these points, the point here and the point on the red circle, and then project them and see where they hit the purple circle. From that I can get a range of angles. If I take all of those ranges of angles from all of the orange circles and union them, I can get a set of ranges, which is all the perimeter that's blocked, and from that I can figure out all the perimeter that's not blocked. Okay? So let's go through some of the math. So, I really want to figure out this angle. If I can figure out that angle, then I know, the center of the orange circle, that's given to me in the input. I know the length of the radius, that's also given to me in the input. I can figure out this angle to the x-axis. I can just use atan 2 to do that because I know the centers of both the red and the orange circle. So if I can figure out this angle, I can very simply figure out that point, and likewise this point. So I can figure out the points that I want on the ray if I simply figure out that angle. Okay? And once again, my standard caveat, this is not the only way to solve this problem. Other people solved it different ways. This is just my simple way of solving it. So, let's look at one of the rays. That black ray is the one we're interested in. We want to know this blue angle, which, by the way, is the same as that angle. How do we know that?
Because those two lines are parallel.
Similar triangle?
Yes. Similar to either one of those is good. The fact is that this is a perpendicular because it's a radius to a tangent. Likewise here, that's a perpendicular because it's a radius to a tangent. And opposite interior angles are congruent. I remember that from my 8th grade geometry, something like that. So those two, if I can figure out that one angle, I've got this point, I've got this point, I've got all the points I need. Okay? So what I'm going to do is going to take that ray and move it so that it's pointing out of the center of the red circle. When I do that, I wish I had a laser pointer. Is there something like a stick?
And a long stick.
I need a pointing stick.
You want to use the rib stick?
No,
that's a long stick.
That's a long stick, all right. That might work.
Okay.
It's kind of heavy. It's kind of,
Let's do it for fun.
I don't know. This thing is dangerous.
It is a pointer.
I mean, I feel like some stupid Conan type of hero.
Post-apocalyptic superhero.
Yeah. Okay, so if we move this that way, so we've added to this, and my artwork is terrible. So this is the radius of the orange circle. We've pushed this up by the radius of the red circle, right?
Yeah.
Well, we know this distance from the center of the circle to the center of the orange to the center of the red. The distance formula will give us that. We know the distance from here to here. That's just the sum of the two radii, right? We know that this is a right angle. Why? Because this was a right angle. Okay, so we've got a right triangle. We know two sides. We can simply use trigonometry, a simple arc sine, to figure out that angle. Once we have that angle, we can get all the points we want. We can get those tangent points. So let me give you your vehicle back. Any questions about that? Is that all cool?
Yeah.
We're good? So, once we have those points for both rays, we can project them to the surface of the purple circle. Once again, multiple ways of doing this. This is simply how I chose it. express those rays parametrically. X equals, some constant plus something times t. Y equals a constant plus something times t. It's going to turn out that the px and py is simply going to be the x and y of the red circle tangent point. And the qx and qy are simply the difference between the orange circle tangent point x and the red circle tangent point x, and the same thing for y. Think about it. What happens when t is 0? What are x and y?
Qx and py.
Which, as we said, was just the tangent point on the...
Right.
So when t is 0, it's just the tangent point on the red circle. If this differences, what happens when t is 1?
The tangent point on the orange.
It's the tangent point on the orange line. So we've got this parametric representation. I should have put that on the slide. But we've got this parametric representation of a line in terms of t. Or actually it's a parametric representation of a ray because we're insisting that t be greater than 0. Okay. So we can take the parametric representation, plug it into that simple equation for the circle. We know the radius of the purple circle. We know its center is 0. So we can take those for x and y, plug it in there. What we get is big and nasty, but it's simply a quadratic in t. We can use the quadratic formula for solve for t. Once we have t, we can plug it into the parametric equations and get an xy that's on the surface of the purple circle. Once we have that, we can just use a tan 2 to get that angle, and that's what we're after. We're after, the range of angles. Make sense? Okay. So from there, it's simply a matter of taking all of those ranges and unioning them. As a matter of fact, I think I have this on a slide. Let's see. Nope, I don't. From there, it's simply a matter of taking all those ranges and unioning them. And that will tell you all the points that cannot see. That'll tell you the proportion of points that cannot see all of the red circle. So take 1 minus that, you've got the proportion of points that can see the red circle. Whew. Any questions? Cool. Let's talk about science. Ford-Fulkerson. This is a more advanced algorithm, but Ford-Fulkerson is just all over this. And I should also, once again, caveat, other people solved it in different ways. There are different, graph properties of graph. There's a certain property of a graph. I don't know the name of it, but people used more advanced graph algorithms on this. Ford-Fulkerson is what made sense for me. So, built a Ford-Fulkerson graph for matching, which has a source, a link from the source to every person. There's a sink. There's a link from every button to the sink. And then between the people and the buttons, there's a link if that XY, that yes-no matrix says that that person can stand on that button. Okay. Simple Ford-Fulkerson graph for matching. So, if we give the edges from the source to the people and from the buttons to the sink a value of k, and if we come out of this with a Ford-Fulkerson max flow of n times k, that means that we were able to put the people, each person, on k separate buttons without interference with each other. That means that the answer is at least k. That means that there are at least k possible solutions. So my code used that with with binary search to figure out what the number was, what the exact number of possible solutions was. You couldn't simply go from there to the end, though. You couldn't simply go from that to to figuring out what the permutations are, because there could be some extra edges, and those extra edges can cause you to get stuck in corners. So you have to eliminate. You have to do this with the optimum k. Once you've done it, you have to go through the links between people and buttons and see which ones weren't used. And you have to remove the links that weren't used in order to keep you from getting stuck in corners. And And from then, it's just more Ford-Fulkerson. You just keep doing Ford-Fulkerson to find a permutation, remove those edges, do it again to find another permutation, remove those edges, keep going for k turns, and that gives you your answer.
So if you already remove the edges that are never going to be used, why can't you use 3D at that point?
You might be able to. As I said, this is simply the way I thought of it. I had Ford-Fulkerson coded up, and I love Ford-Fulkerson, so there you go. Might be entirely possible to do that.
Okay.
I'd have to think about it. I haven't thought about it.
Yeah, actually, we tried greedy during the contest, and you know, it's an epic fail. Like, we got like 4 or 5 incorrect submissions for that.
Yeah, but the problem, once again, the problem is those extra edges that cause you to get stuck in corners.
Yeah, like I think like for network flow programs, it's usually like it seems you can do greedy on it, but when you actually try greedy, you get a lot of wrong answers for that. Yeah.
Tapraj has pointed this out, that greedy algorithms are tricky. Greedy algorithms most times are easy to code up, but difficult to prove to yourself that they're actually correct.
Right.
And so it can be, you can end up, at the end of the contest with an extremely difficult problem that has, code that big.
Yeah, like A.
Also, is there a particular reason to use Ford-Fulkerson, or could you?
I love Ford-Fulkerson. That's the reason. That's all. That's how I saw the problem.
Okay.
Just my personal prejudice.
Okay.
There are, as I said, there are other people that use different graph algorithms having to do with, I forget the term, invariant graphs or something like that. I forget the exact term. But other people use more sophisticated graph techniques. Ford-Fulkerson worked for me. The worm and the apple. There are 2 parts to this. The first thing is you have to build a 3D convex hull around the points that you're given. And then the second part is that you have to find, for any given point, the face that it's closest to. Okay? So there are a lot of algorithms, and we also, the numbers were large enough that we had to use an algorithm for the convex hull that was order n squared or less. If you did anything more than n squared, you would have timed out because there were up to like 1,000, I believe, points. So there are a lot of convex hull algorithms out there. And I know a lot of people who skipped this because they didn't know one. But I want to show you that you can think through this and you can come up with one even if you don't know the canned algorithm. Okay? So this is, first find the point with the smallest z value. Translate all points so that this point is at the origin. So take your apple, find the smallest z, and translate it so that the smallest z is at the origin. And I should say that you can use lazy translation, which means you only need to translate a point when you're about to use it. You don't have to have an order n loop that goes through all the points and translates them. You can wait until you actually need to do it to translate them. Okay. Now, find the point that has the smallest angle with the xy plane. Think of it as like a rolling soccer ball. If I were to roll this soccer ball, which point hits the ground first? So look around from that point that's at the origin for the point that has the smallest z. Whichever one has the smallest z, that edge is guaranteed to be on the convex hull. Okay? So we're going to take that edge, we're going to rotate it around the z-axis in the xy plane so that it sits above the x-axis. Then we're going to rotate it in the xz plane around the y-axis so that it sits on the positive x-axis. Okay, so we've taken that edge and we've rotated the figure so that edge, one point's on the origin and it goes along the positive x-axis. Cool? Whatever has the smallest angle in the YZ plane, that's the third point of your face. So go through all the points, figure out which one has the smallest angle. That is the third point of your face. So that gives us our first face. We've got one face with 3 vertices and 3 edges. We cool so far? And once again, nothing terribly advanced about this. This is just sitting down and thinking about it. Okay. Cool? So now we're going to proceed like a breadth first search. We're going to take our edges and we're going to put them onto a cube. And then for every edge is going to lie between two triangles. We're going to know at least one of them. That's how it got on the cube in the first place. If we know the other one, we can simply skip this one and go on to the next one. But if we don't know it, we have to find, that second triangle that edge abuts. Make sense? Okay. So we're going to pull the same trick. We're going to move one point to the origin, rotate it so that the second point of the edge is on the x-axis, and then we're going to pivot it around YZ so that the other point is in the negative y direction. So we're going to rotate this thing so that face, that triangle, the one we know, is in the xy plane where z is equal to 0. And then we're going to pull our same trick of finding the smallest angle. Whatever is the smallest angle, that's the third point of the other triangle. Okay. That gives us another face. That also gives us two more edges to put on our cube. Make sense? That's it. That'll give us the convex hull. Any questions about that?
It seems like you do a lot of rotations. Doesn't that introduce a lot of double precision errors?
We set the precision, well, first of all, the rotations are fairly simple. They do use sine and cosine. But aside from that, it's simply sine, cosine, 2 multiplies, and an add, or a subtract. So it's not a very complex operation. Anytime you do a lot of operations with double, you run the risk of round-off error. No matter what you do, no matter how you do it, you're going to run the risk of round-off error. But we set the accuracy to be 4 decimal points. So you didn't have to be too terribly accurate. And as I said, this problem had 3 submissions. Want to guess how many of those were correct?
All 3.
All 3. There were no incorrect submissions of this problem. And this brings me to something that I should mention. If you take a look at my code, there's some stuff that's commented out. What we do, we ask for 4 decimal places of accuracy. There's some code in there commented out that takes it to 7 decimal places of accuracy, then looks and see if it ends with 500 or 499. If it ends with either of those, we eliminate the case. If it's too close to a cusp, if it's too close to where we might have round-off error, where somebody might just round off slightly wrong, we completely eliminate the case. Okay. And we did that with red gem also. So once we do that, we've got all of our faces. For every face, we can record the XYZ translation and the XY, XZ, and YZ rotations of what we did to get that face flat on the XY axis. And from there, we can do the queries. So for every query, all we have to do is take the point, and for every face, do those translations and rotations, and then whatever its z value is, that's how close it is to the plane. I know there are fancier ways to do this with dot products and normals and things like that. This is something that works, and it's not terribly time consuming. It's 3 adds, 4 sine cosines, 4 multiplies, and 2 more adds, and for every face, which isn't terrible. There are faster ways, but it isn't terrible. Okay. So once you do that, and another thing, you may think you have to check to see if the point, once you've got the face lying on the XY plane, does the point actually lie directly above or below the face? You actually don't have to do that, because the smallest distance is going to be in the middle of a face. There's absolutely no way the smallest distance can be off of the face that it's closest to. Okay, so you might get a value that is not quite right because it's the distance to this plane, but the face is over here, but it won't shortcut the best answer. The best answer will be where it's in the middle of a plane, and we'll get that. Okay. Any questions about the worm in the apple?
How many triangles did you have in the worst case? How many triangles did you have in that convex hull?
I don't recall, but I believe it was in the neighborhood. I know we had some cases that were over 100. I don't recall whether we had any in the 200 to 300 range. Yes.
So as a general rule of thumb, if you do have 1,000 points in 3 dimensions, how many triangular faces will be on a convex hull? Like, we just sort of should be n.
No, there's this Euler Poincaré formula that says that it has to be twice the number of vertices. So it can be a maximum of 2,000. If all the vertices were on the convex hull, then you can have twice the number of triangles, approximately, plus minus 4.
Yeah, a lot of our data was randomly generated, and so there are a lot of points that were inside. And also, we guaranteed that no 4 points were coplanar, which made things a lot easier. That guaranteed that the faces were triangular.
Yeah.
I believe that this solution will work even if there are coplanar points, if there are a series of triangles that form a more complex face. But didn't need it. We promised that they were not coplanar. Anything else?
Any questions, guys?
Well, that's the entire problem set. Do you have any questions about the problem set just in general, or the contest in general, or anything in general? You're good?
Hey, thanks, vanb.
Well, thank you for inviting me and giving me this opportunity, and I hope to see you at Southeast Regionals next year.